about carbocation rearrangement. And this is something that can happen now anytime you have an intermediate in your reaction that is a carbocation. So SN1, E1, these are types of things you need to be aware of. And I showed you a situation where rearrangement can occur. You see the presence of non-rearranged products, but also this weird rearranged product where it appears that a methyl group has just moved over. And one of the important structural patterns for when carbocation rearrangement can occur is when you have a secondary carbocation adjacent to a tertiary or a quaternary carbon. And the reason this can occur is because of the sigma to p hyperconjugation that allows the electrons in an adjacent carbon-carbon bond to spread out into the nearby empty p orbital. You go through a transition state that looks like this, where the methyl group is halfway between the two carbons, evenly sharing its two electrons with both of those two carbons, with some partial positive charge on all of the carbons. And then finally, this next intermediate where the methyl group has literally moved over. This is this process of, and this is a transition state, this process of going from a secondary carbocation to a tertiary carbocation with movement of a methyl group. That's what we mean by carbocation rearrangement. And we'll have a specific way of talking about that. We'll say that the methyl group moved from carbon 1 to carbon 2. Carbon 1 is the original carbon the methyl group was on. Carbon 2 is where it's on after the rearrangement. And we will call this a 1,2 methyl shift. But carbocation rearrangement is not limited to methyl. It could be hydride shifts, that is a hydrogen moving over. And it can also be an alkyl shift, that is an alkyl group moving over. Okay, so the kind of question you can expect to see on this subject might be, like that's on the quiz before you, here are some products, explain how each one forms, where you have to come up with a mechanism that accounts for the formation of all the products. Alternatively, you might be asked, predict the products with a starting material like this, where you have to predict the possibility of carbocation rearrangement. And again, how do you know when that's going to occur? You look for secondary carbocations adjacent to tertiary or quaternary carbons. And the reason it happens is because it allows you to go from a less stable secondary carbocation to a more stable tertiary carbocation. All right, questions about that? Yeah?
Does it need to be the methyl group that's moving?
Does it have to be the methyl group that's moving? In this particular example, yes, because there's nothing else that could move. However, if we were to change the situation slightly to where there was a hydrogen, and we were to do basically the same reaction with HI. Remember, we expect HI to protonate the alcohol, thereby turning it into a fire-leaving group. My kids are impressed that I can pull that one off. I don't know if I actually pulled it off, but anyway, turn OH into a great leaving group. Then we learned that for secondary and tertiary alcohols, the leaving group leaves to give you a carbocation. Again, here you have a situation where you would have a secondary carbocation adjacent to a tertiary carbon. And here, to decide what to do, you simply ask, which group should I move to do a rearrangement that allows the less stable secondary carbocation to convert into a more stable tertiary carbocation? If I moved a methyl group, that would put the positive charge over here and it would still be a secondary carbocation. So the right thing to do is to move the hydrogen with its electrons. That's called a 1,2 hydride shift. It again happens because of sigma to p hyperconjugation between that CH bond and the empty p orbital that's on the positively charged carbon. The 1,2 hydride shift literally involves the hydrogen leaning over and then becoming attached to the other carbon, and then the positive charge is here on the tertiary carbon. And so for products, you would show the products that come from the lack of rearrangement, just the non-rearranged product, and then you would show also the rearranged product where the iodide is now on the different carbon. Okay? So that's an example of a hydride shift. But again, the pattern you're looking for is positive charge adjacent to a secondary, a tertiary or quaternary carbon. If it's adjacent to a tertiary carbon, you can do a 1,2 hydride shift. If it's adjacent to a secondary quaternary carbon, you can do a 1,2 alkyl or methyl shift. All right, other questions? Should we practice? Here's something on the quiz. Dun, dun, dun. Which, it's not really that stressful. You get credit just for showing up and trying. So, here is a question in the format of draw a mechanism that accounts for the formation of all of these products. I will give you a hint. These two are non-rearranged, and this one is rearranged. All right, so go ahead and get started on that one. See if you can account for the formation of all of those products. What? Oh, you want a hint. Okay. Okay. Okay, do you still need a minute? Yes? Yes? Okay. All right, just a question for you. Here, we've got a secondary alcohol. We've said with HCl, the mechanism tends to be SN1. By the way, why don't we see any elimination products? We're like, I don't know, we don't know. We just don't. Probably it has to do with the fact that Cl- is a really, really, really weak base, but your text doesn't necessarily explain that. And so we just have to be okay with the discomfort there. You know that it was an SN2 process for two reasons. First, you see two configurations of the chloride, right? Second, you see rearrangement. Both of those things are indicators of carbocationic intermediate. So, what should the first step of your mechanism be? Protonate the alcohol. And this is a fast first step. This is a sort of equilibrium step. You're first protonating the alcohol to get the positively charged oxonium ion. Good. Then what? You know that the chloro doesn't come in and attack at this stage, because if it did, that would be SN2, and we would get no rearranged product, and we would also get none of this stereoisomer. So that tells you that the leaving group had to leave. Remember, good leaving groups are conjugate bases of strong acids. The leaving group here is water, which is a conjugate base of a strong acid. Okay, so here is our carbocation. Now what? For the non-rearranged products, what do I do? Yeah, we just have chloro attack from above or below. That's pretty good. And that will give me those products, no problem. Now, if I wanted to do the rearranged products, I got to start from the same carbocation, noticing that I have a secondary carbocation adjacent to a tertiary carbon. So, how do I show a rearrangement? This is something we didn't necessarily talk about. We know that the hydrogen starts, which is already hyperconjugating with the empty p orbital on this carbon, starts to lean over. The way you show a rearrangement is simply to take the electrons in that carbon-hydrogen bond and move them over to the other carbon, and the hydrogen goes with it. Yes? Right. How do you know whether it's that hydrogen or the methyl group? Two reasons. First, in the product, there are two hydrogens here, whereas there was only one before in the non-rearranged products and in the starting materials. So that's an indicator that the hydrogen moved. Yes. Could you predict it without seeing it? Absolutely. Let me draw the rearranged product that would come from the rearranged carbocation that would come from a 1,2 hydride shift. And then I will draw the hypothetical product that would come from a 1,2 methyl shift, and it will be very clear why it has to be this way. All right, so look at that carbocation. Now let's imagine that it was the methyl group that shifted over. What's the difference between those two options? This is a tertiary carbocation that is more stable. This is a secondary carbocation that's no more stable than the starting one. So rearrangements, for our purposes, the rearrangements that I ask you to predict will always lead to more stable carbocations. So if the methyl group were to move over, instead of the hydride, the positive charge that would be left behind by the methyl group is on a secondary carbon. That is no more stable than the secondary carbon we started with. So that 1,2 methyl shift is not preferred because it doesn't lead to a more stable carbocation. So the types of rearrangements I ask you to predict will always be ones that lead to a more stable carbocation. Okay, once you've done that, yes?
Is it always true for halides that they won't do any elimination products?
Is it always true for halides that they won't do any elimination products? Won't or ever or never is such a strong word. If you were to do this in the lab, I wouldn't be surprised to see elimination products. Since they're showing you in this book trends and not actual data, it's difficult to say. If you were to dig deep in the chemical literature, my guess is you would find elimination products. But we're going to assume it works without trouble.
So as far as predicting products, whenever we have a halide, we're not going to predict any elimination.
Yeah, when you have an alcohol reacting with HCl, you're not going to predict elimination products.
What about if it's not alcohol?
What if it's not an alcohol? I don't know. I can't think of any not alcohol that you would use HCl as a starting material for, though, because the whole purpose of HCl is to protonate the alcohol to turn it into a good leaving group. Yeah?
So the 1,2 hydride shift, that is more stable because having the methyl group on the carbocation is going to like stabilize it more because
Yeah.
like the inductive effect or
Yes, we learned two things that make more substituted carbocations more stable. The first was the inductive effect. Alkyl groups are electron donors to electron poor sp2 hybridized carbons. And the second was more opportunities for sigma to p hyperconjugation that are possible when the carbocation is more substituted. So to show that mechanistic step, you would simply have Cl minus attack from above or below, and you would get this rearranged product. By the way, notice that I did not bother to draw dashes or wedges on that rearranged product. I could have done, but that carbon's not a stereocenter, so no matter whether I draw a dash or a wedge, it's the same thing, and so it's totally fine to not use dashes or wedges when the carbon is not a stereocenter. Yes?
Just to clarify, so does the chloride ion attack the positive charge at the same time that the hydrogen is moving across, or is it two like different?
Good question. Does the chloride attack the positive charge at the same time as the hydrogen is moving across? No, it happens after to get to this product. So hydrogen moves, you get another intermediate, and then chloride attacks. Yeah? So which would be major or minor? That's difficult to say. probably you would maybe hypothesize that the rearranged product should be the major one because it goes through the more stable carbocation. But I'm not going to ask that question. I'll simply ask you to draw all of the products, both rearranged and not rearranged. But don't be surprised if your text only shows you the rearranged one. Okay, good. So this kind of thing can happen. Carbocation rearrangement can happen basically any time you go through a carbocationic intermediate. So we've dealt with substitution reactions of alcohols that go through carbocationic intermediates. Now we're going to deal with elimination reactions of alcohols that go through carbocationic intermediates. And then we're going to talk about ways to sidestep the carbocationic intermediate. But this reaction is called alcohol dehydration. And you're going to see that in alcohol dehydration, we get E1 products only. So again, this is going to defy what you've expected from chapters 7 and 8, where we taught you that SN1 and E1 products always compete with each other. This is going to be another example where you see elimination products instead of substitution products, just like what we did previously where you saw only substitution products. So that's a minor detail that you're just going to have to get comfortable with. If you have to memorize it, that's fine. We don't really have a great explanation for it. You've actually seen an alcohol dehydration reaction on your exam. The starting material was this, and then the product was this. And so the starting material loses water, and you end up with a molecule that has an alkene in it. But this requires an acid catalyst to have happen. The reaction, it turns out, is actually an equilibrium reaction. It can go forward or reverse depending on the conditions. One of the ways you can make this reaction go forward is the fact that alkenes have a much lower boiling point than alcohols. So you can actually use a procedure called distillation to separate the alkene product from the alcohol starting material and by doing that, using Le Chatelier's principle, you move the reaction in the forward direction. So let's talk about the acid catalyst. Actually, now that you know that OH is a terrible, horrible, no good, very bad leaving group, it makes sense why you would need an acid catalyst to first convert the OH into a good leaving group. So let's talk about what that catalyst tends to be. There are two options that your text shows you. One of them is cheap but highly destructive, and the other is more expensive but perhaps more commonly used. So the one that your text will use is H2SO4, sulfuric acid, which you learned about in Gen Chem. We can draw the Lewis structure of sulfuric acid this way. It's got 2 protons to lose. The first one has a very, very, very low pKa. And so it's very reactive, and in fact, it's not necessarily a preferred reagent in organic reactions. If you're not careful, it can do other undesired side reactions that turn your starting material into a sort of disgusting black goo. You put sulfuric acid on sugar and it makes like tar somehow. It's kind of crazy. So it's not necessarily the preferred reagent, and it always comes in water. You can't buy pure sulfuric acid. It's always in an aqueous solution. And so it's not a great strategy if your starting material or your products aren't going to be soluble in water. So we need an organic acid, an organic soluble acid that's about the strength of H2SO4. So turns out you can do this. You take the acid structure of H2SO4 and then you put it on a benzene ring with a methyl group. This is called para-toluene sulfonic acid. But because that is so long to write and say, we abbreviate toluene and sulfonic with TS. And then we put an OH there to indicate that it's an acid. And you can think of this as, this has a pKa of pretty close to -11. So it's a very, very strong acid. It's like the organic soluble version of sulfuric acid. And there are practical reasons why you would use one versus the other, but you can use them interchangeably. You ought to be able to recognize them both. All right. So with that, as I draw a mechanism, I'm just going to use HA, but understand that when I write HA, I'm referring to these two acids. Okay? So our mechanism for this reaction would be first, HA protonates the OH group. To give you the oxonium ion. I'm not showing dashes or wedges because this carbon is not a stereocenter, so the stereochemical configuration doesn't matter. Then we show the leaving group leaving. The evidence that the leaving group leaves actually comes from the fact that you do see carbocation rearrangements in this reaction. Not this particular reaction because there's no rearrangements that can occur here, but in other molecules like I will show you, if you do acid catalyzed alcohol dehydration, you do see rearrangements, okay? So far the steps are identical to what we saw before in the HCl reaction. We protonate the OH to get to an oxonium ion, and then the leaving group leaves. So far that's just the first step of the SN1 reaction. At this stage though, instead of doing a substitution reaction, we do an elimination reaction. Now, let's point out, if water attacked that positive charge, you'd go back to this oxonium ion and perhaps back to the alcohol. And in fact, that's happening all the time. That's an equilibrium reaction. It can go forwards or backwards. But if instead the conjugate base of your acid removes this beta proton, that gets you to the alkene product. Now, another question that you might ask is, why doesn't the conjugate base of the acid attack the positive charge like Cl- did in the reaction above? And the answer is, actually, that probably does happen, but you can run the reaction under conditions where it doesn't, especially if you're isolating the alkene by distillation, and your text doesn't talk about that issue at all, so we're just going to ignore it. Okay, questions about this? Yes?
Can you help me understand why this one would be only elimination, the other one would be only substitution for?
Yeah, so the question is, why would this give you only elimination, whereas the one we did on the quiz did only substitution? In order to explain that, I have to give you hand-wavy explanations because there's really not an explanation given in your text. The hand-wavy explanation I gave you for using HCl is that Cl minus is a really, really weak base, so it's not going to do elimination reactions. You could make exactly the same argument for the sulfuric acid and the toluene sulfonic acid materials. They're conjugate bases. A minus are really weak bases. So the answer is I don't know, and that's probably a detail you have to memorize.
So in these cases, would you show us like the product and ask us to predict the mechanism?
So I could always show you the product and have you predict the mechanism, but I could also give you starting material and reagent, and you'll have to memorize what the products are.
What is the rule there?
There are going to be, so what I'm saying is there isn't a rule to learn here because your text doesn't give you one, and I don't know what it is. But you can memorize that HCl, HBr, and HI give you substitution products with alcohols, whereas sulfuric acid or TSOH don't. There are going to be a few things like that in this chapter where is the underlying rule and how would I have known that and predicted it? And my answer is going to be, I don't know. And it's unsatisfying. Just a second. But it turns out chemistry, because we're still learning things, you often find a reaction that's useful and works. You're not 100% sure how it works, so while you're continuing to research how it works, you're still using it to do useful things. And these may be examples of some of those kinds of reactions. And people have likely studied these reactions in more detail, but these are all the details that they've given us in an introductory course. Okay, yeah, go ahead.
Is the only defining feature or the base used in these two determine? Sorry, is the only difference just which base you're using? Is that what?
So is the only difference, right, you're using an acid, the difference is the structure of the conjugate base of the acid. For HCl and HBr, it's an HI, you've got the Cl minus, Br minus, or I minus. Those can be good nucleophiles, generally not good bases. And what we're saying here is that somehow the conjugate bases of sulfuric acid or toluene sulfonic acid are generally, they are not going to be nucleophiles for reasons that are not clear and not explained. And there's no reason you would have been able to know that other than I told you what the results are. Yes?
For alcohol dehydration, does the carbocation have to be, I guess, does that have to be more substituted or less?
So for alcohol dehydration, does the carbocation have to be more substituted or less? The carbocation would need to be either a secondary or a tertiary carbocation. If it was a primary carbocation, the reaction would still work, but you would predict an SN2 mechanism because the leaving group couldn't leave to give you a primary carbocation. All right, let's also show you how rearrangement is possible with alcohol dehydration. So I think this is something I put on your problem set. This one is fun, so buckle up because we're going to do a few different things here, different kinds of rearrangements. So already from the beginning, you should be expecting some kind of rearrangement here because you have a secondary alcohol adjacent to a quaternary carbon. And if we were to go through a carbocationic intermediate, that would be a situation where rearrangement could occur. I'm going to use TSOH, and you're going to have to remember that that's a strong acid like sulfuric acid. And you're going to have to remember that its conjugate base is not a good nucleophile for whatever reason, and so we don't expect to see any substitution products here, only E1 dehydration products. And by the way, if you're like uncomfortable with results that just are, that don't have explanations, welcome to research. Like, this is what people do research about, to try to understand mechanisms of reactions. And sometimes we don't have good answers at the beginning, but sometimes reactions are useful nevertheless, and this is one of those cases. So first, you would protonate the OH to convert it to a good leaving group. And we're going to do this question in predict the products format, which is we're not sure what the products are, we have to predict them. Sometimes using mechanism is a great way to predict the products. If you understand the mechanism, you can figure out what the product should be. We just protonated the OH group to get this oxonium ion, which now has the fire leaving group. So we'll have the leaving group leave, and that will get us to a carbocation. And anytime we see a carbocation now, we need to be looking for the possibility of rearrangements, but we're only going to worry about rearrangements if they get us to a more stable carbocation. So I'm noticing a secondary carbocation adjacent to a quaternary carbon. That is a classic situation in which I could expect a 1,2-methyl or a 1,2-alkyl shift to allow a group to lean over and become bonded to the positively charged carbon. All right? Now, we're not going to worry at all about the possibility of one of these two hydrogens moving over and doing a 1,2 hydride shift. Why am I not worried about that at all? It would just give me a secondary carbocation with similar stability. So that's probably not a major pathway for this reaction. We're not going to worry about it because it doesn't lead to a more stable carbocation. Good. So let's draw. Since this is a dehydration reaction, let's draw products let's draw dehydration products that are not rearranged, and then let's draw rearranged dehydration products. One not rearranged dehydration product would be if the conjugate base of our acid removed this beta proton, and then that gave us this product here, which is a non-rearranged product. Okay, that's fine. But then let's deal with the possibility of rearrangement. All right, so here is your carbocation. There's two different kinds of rearrangements that can occur here. One of them should be pretty clear to you, and the other is going to blow your mind. And you're going to say, I didn't know that was possible. And I'd say, welcome to OChem, baby. So which is the one that is straightforward? What should I do to rearrange this to a more stable carbocation? What's going to lean over? One of the methyl groups. Doesn't matter which. One of the methyl groups is going to lean over and form a new bond with what used to be the positively charged carbon. The methyl group's going to move over from carbon 1 to carbon 2. We will call that a 1,2 methyl shift. Notice how that, and I'm going to stop using dashes or wedges at this point because you will see in the final product what we've got are not stereocenters, so we don't need to worry about the stereochemical configuration of the intermediates. Notice that when that methyl group hops over it moves the positive charge over to carbon 1, whoa, where it is more stable on a tertiary carbon. So this is a more stable tertiary carbocation. Okay, now I must consider the E1 elimination products from this carbocation. So now we're back to sort of chapter, chapter 8. What we want to do is identify the various beta protons that are present, and there are 3 of them. Orange, purple, and green. Those are very Halloween-y colors. If I remove the purple beta proton, I get this product. If I remove the green beta proton, I get this product. And if I remove the orange beta proton, I get this product. Of those options, which do you think is the more stable alkene? Orange, yep, more stable, more substituted. It's probably a major product because it's more stable. Okay, so that is good. And on you want to predict the products question, you would need to select all of those answers as possibilities. Now, there's one more. But before we do the one more, other questions? Yes?
We need to know which one is going to be, obviously we know that one's more stable, but we need to know which of these 4 products is going to be the most stable out of all.
Do you need to know which of the products is going to be the most stable of all? I mean, the only decision point on that, I would say yes, is because you can identify the more substituted alkene. As to whether rearranged versus not rearranged products are going to be dominant, we're not going to worry about that. Okay, so let's go back to the carbocationic intermediate because this was rearrangement 1. Now we're going to do rearrangement 2. And you'll see in retrospect that there's no reason that this can't happen. You just didn't know that it could happen. So I told you before about the possibility of 1,2 methyl shifts and 1,2 hydride shifts, but now we're going to consider 1,2 alkyl shifts. If this methyl group were something else, if it were, say, an ethyl group, could it still move over? It's fine, it just leans over and whatever else it's attached to comes with it, right? What if it were a propyl group? What if it were really long? Can it still do that? Sure. What if it were tied back around to the other side of the molecule? Can that happen? The answer is yes. What? So, imagine that this carbon here, and imagine that the molecule twists so that this carbon-carbon bond is hyperconjugating with the empty p orbital. To do that, we would probably need to adjust the way this molecule looks, and we can do that if you want. Maybe the molecule would need to twist around so that this was a wedge, or a dash instead of a wedge. We're talking about minor rotations around carbon-carbon bonds. But yeah, this carbon-carbon bond can totally overlap with the empty p orbital that's on the adjacent positively charged carbon. It starts to lean over, and then it's going to form a new bond. Now, it can be helpful with these kinds of rearrangements, and this is called a 1,2 alkyl shift. It can be helpful to number your carbons so you don't get mixed up. I know this kind of thing blows your mind because you haven't seen it before. If you practice it enough, it'll be like, okay, I see what's going on. I'm going to number the carbon where the alkyl group in red used to be as carbon 1. Then this is going to be 2, 3, 4, 5, and 6. Now, the arrow indicates that I'm breaking the bond between 6 and 1, and I'm making a new bond between 6 and 2. So what I recommend when you do this is you keep everything in the same place. You draw a new long bond in red between 6 and 2. You leave the bond between 1 and 2 in the same place. But now 1 is no longer forming a bond with 6, and 1 should have a positive charge. You don't believe me, do you? Yes?
Is it gonna look not really be a long bond? Is it gonna kind of shift over them like?
Yeah, you're exactly right. It's actually gonna be like this, but sometimes if I were to jump from this to this, you'd be like, what on earth just happened? And so we're just trying to draw it at a level that at least keeps track of the connectivity so we can see what's going on. All right, we'll pick up there. Don't forget to turn in your quiz on the way out. Just stack them up right here.